Here's part two of our videos of finding derivatives using the power rule, and now we're going to add kind of also the sum and differences. But let's take a look at another example here. And so we have y equals square root of x. And so in this case, what we need to remember is square root of x can also be seen as a 1/2. And so as we look at this example here, we're taking the derivative of x to the 1/2. The same mathematics happens. This is the exponent, comes down in front, and then right there, that's 1/2 minus 1, which is negative 1/2. And so your derivative is 1/2 x to the negative 1/2, or you can see it becomes this or this. All of these are equivalent expressions, and so that are equal to each other. So keep that in mind. You can also have something where it's a decimal. Same rule applies. 0.7 subtract 1, negative 0.3, and then you have that. Of course, that could also be, we could say 7 over 10 x to the 0.3, or you 0.7 over x to the 0.3. I mean, again, a lot of different ways to kind of represent that. So the same rules would apply in that case. Theorem 2, we kind of talked about that earlier when we did the derivative of pi squared with respect to x equals 0. Here the derivative of any constant equals 0. And so just know that anytime you take the derivative of a constant number, of some number, it equals 0 because there is again no rate of change. The constant doesn't change. And so that's why we would say the rate of change is 0 in that case there. We have another theorem in terms of sometimes the functions are multiplied by a constant, and so what that says is, let's say I have f of x equals 2x squared. F prime of x would be equal to 4x. Another way we could have seen that was, let me take the 2 out of there. So I could also see f of x equals 2x squared. I could see that as 2 times x squared. And so if we take, based on that, it's 2 times the derivative of x squared dx. And so in this case, you get the same answer. 2 times 2x equals 4x. And so that's all that's saying, is that this constant doesn't really change the result. You just use using to multiply. And so let's look at that. So in this case, again, if you wanted to think about it, you could break this up. This piece can be broken up. You can break that up when you find the derivative and then multiply the 7 after. You can always take a constant out and then just find the derivative of the variable part. And so you can see if you do that and then multiply that derivative back, it's not changing the answer. The answer is still 7 times 4 is 28. Just a slight different way to do it. Notice we're taking the derivative only of these parts here, only of the variables, and then leaving the constants out of it. And so because of that, it's just another way to look at the derivative, and that's what this formula is saying. And so you can take the derivative of that using the power rule or using this rule here, a combination of that. So on these, again, these quick checks, if you look at it, the answer is still 9 times 10. But again, just to emphasize it, y equals 10x9. What you could do is just find the derivative of x9 with respect to x, and that would be equal to 9x to the 8. And then you multiply that by 10, and so you get 10 times 9x to the 8, which is 90x to the 8. And so you get that same answer, but we get that same thing by doing 9 times 10, 90, and then x to the negative x to the 8. So then again, that's your related to your power rule, and so then you end up with that. So again, take a look at those and how that gets done. Another thing to observe here, when you have that variable in the denominator, many times we move it up to calculate the derivative. Use the negative exponent because it's easier to take the derivative, and so that's what you would do in that case. Whenever you have that exponent in the denominator, make it a negative exponent. That allows us to do that. And then the last thing for this addition to this section is the derivative of two functions that are added or subtracted together. You can just take the derivative of each of those and then combine them. So for example, the derivative of 5x cubed minus 7 is going to be equal to, where is it? Oh, coming down here. We'll do b after. You just take the derivative of each of these separately. If you look carefully, this just becomes 15x squared. The derivative of 7 is 0, and so there is your derivative right there of this here. So you can take what this sum and difference rule allows us to do is to find the derivative of each of those separately, and then you can use the power rule with that. Same thing here. Notice what we're going to do. I would turn this into a 1/2. This turns into x to the negative 1. It's easier to find. And then you go ahead and find those derivatives using the power rule. And then you can go ahead and you get that answer there. And so again, for a quick check here, looking at a quick check before you look at that answer there, because if I scroll up, your answer is going to come up. That first one, just without looking at the answer, I can see that the derivative of that's going to be 15x4. This here, well, let me rewrite it. I would rewrite the function for y. I would say y is equal to 3x5 plus 2x 1/3 plus square root of 5. This is a constant. You don't need to put it to the power 1/2. It's a constant. We know the derivative of that's going to be 0. And so you just take the derivative of that. So without showing that answer down there, again, I can see that it's going to be 15x4 plus 2/3. And in my mind, I'm looking at 1/3 minus 1, 1/3 minus 3/3. So this is negative 2/3. So that's the answer we should get. Again, there's kind of the long way that you could break it down. If you want to pay attention, this becomes a 0 right there. And so then you can see we end up with 15x4. Did I miss? Oh, I missed this one here, so I can't forget this one here. This one here would be plus 1/3 x to the negative 2. So then you end up with that negative 2/3 there. When you subtract 1, x to the negative 3. So you end up with that there. And so that's kind of the extra part. Then again, you're using the power rule. You're just doing it multiple times in the same expression. So that's what you got there.